again. Welcome to another user story of Apache Doris. So in the previous sessions, we've covered different aspects of Apache Doris, like AI pipelines, real-time analytics, and the like. And now we've come to IoT and observability. One of the use cases where Apache Doris surprises its users most. And with this topic, we have Greg with us. And Greg has spent years in the EV industry, and I bet his insights and experience will bring great inspirations to us all. So, Greg, we are ready to be impressed.
Wow, that's a lot to live up to. Thank you, Shirley. Hi everyone. My name is Greg Svitek, and my topic today is about EV charging and IoT, and basically how you're able to use Doris as an observability platform to basically be able to get real-time insights and alerting, and what that would look like. And for this talk, we're going to use a real world EV charging problem that happens every day. But this could also be applied as well to general IoT devices as a whole. So a little bit about me. Currently, I am the chief software architect for a company called WorkWave here in the United States. WorkWave is a SaaS product that's used by the pest control and cleaning industries and lawn care, where basically our products run their entire business. It's basically their back office solution to schedule technicians. And then once the technician arrives, they have a mobile app that instructs the technician to what the work orders that they need to basically go off and carry out. And then from there, from there it then goes into accounting and handles all those things. And it also uses a data lake on top of it to provide actionable insights. This is used by some of the largest companies in the United States for these specific industries, and we are the leading provider for those industries. But prior to joining WorkWave a couple months ago, I spent a lot of time in the EV charging and mobility space. Specifically, I worked for a company based in San Francisco in Silicon Valley called Terawatt. And Terawatt's goal was to basically build really large scale EV charging fleets that has anywhere from 15 to 30 chargers at a facility. What Terawatt is most known for is Waymo, the autonomous robotaxi company that's spreading throughout the United States. Waymo uses Terawatt to provide their charging so that they can run their operations in multiple locations. And the picture you see here this is an example of an EV charging depot that Terawatt provides. And then I also worked up until a couple months ago for a company called Iona. Iona is trying to build the largest EV charging network in North America. It's a joint venture between 8 of the largest auto manufacturers in the world. So Honda, I'm going to skip one, because I'm trying to go fast. Hyundai, Toyota, Mercedes, BMW, GM, Stellantis, and I can't remember. But anyways, they're trying to deploy 30,000 charging stations throughout North America, and they're on their way to doing that. And then prior to that, I worked at a company called Spot Hero, which is the largest online marketplace for parking, and where we built the first ever machine learning models for dynamically pricing parking. The commonality between all of these, though, is all these require data lakes or data lakes. So I've used Databricks. I've used Trino in the past, and I'm currently using Snowflake. So my point here is that for this specific use case, we're going to talk about here, it really applies very well to EV charging and IoT. But I also have the purview of a lot of the other competitors in the space, and this is why I chose Doris for this. I might have chose Doris in the past for these specific applications. So what is the problem in EV charging? Well, in the United States, public EV charging, like fast charging, has a significant first time success problem. So right now, when someone goes to plug in the United States, and a charger that's used in public, similar to a gas station, you have a 70 to 85% chance of it succeeding. So you basically have anywhere from a 30 to a 15 to 30% chance that it won't work on the first time. And I'm going to kind of go through the reasons for that here, how to basically address that part. So just to back this up, so there's some statistics about this. So there's an EV charging reliability report that 71% of the time that it works on the first time. And JD Power in the United States, who is a well-known analyst firm, says that they report 84 success rates in Q1 2025. So it's getting better. I can tell you this, it is getting better, but there's still a big gap, because if someone's trying to decide between you buying, a ICE vehicle, like a gas power vehicle versus an EV, you don't have these issues with gas. So, and then furthermore, JD Power did a second study that 14% of the time that owners who own EVs don't get a charge, and they have to abandon and go to a different location. So this is a significant problem from a customer standpoint. And really, why is that? So the thing that people don't realize with EV charging is it's actually there are 6 different systems that requires for an EV charging session to occur, right? And the complexity with that is these 6 different systems are probably made by different people that don't really necessarily have official business relationships, and they have to interoperate and talk to each other. And then the other part about it too is each of these different systems are really complex technology stacks in itself. So an EV, if you think about it, is a battery management system that requires a lot of software, firmware to make that all work. A charger has their own many components in there. There are many different firmware components to make that work. A credit card terminal, a mobile app, and even a cloud backend and a cloud backend to gather some of this data. And then lastly, for payment, there's payment gateways. In order for this to work, it all has to work seamlessly, very, very quickly. And the entire process usually requires 50 message exchanges between any one of these, depending on how the user starts the charging session. And any one of a failure in any one of these 50 message exchange breaks the whole session. And the other thing here is that because these are all made by different people, there isn't one system that brings all the data together in one spot to even diagnose what's wrong. And that is the real problem. So, but a lot of people say, well, what could break? And really it comes down to 6 different things, anything from the physical connection of the plug being wrong, the handshake when you plug in the EV, communicating back and forth, timeout issues, the protocol that's implemented by the EV to make the EV talk to the charger, that might be wrong for that specific vehicle. There's many authentication failures, and you can see this list can grow. And the real problem in all of this is, if you think about it, every EV, in the US, there are 60 different EV models, right? Each one of those can have their own different firmware version. So every EV that pulls up to a charger can have different firmware versions, which can make all this different compared to the same make and model year pulling up to right next to it and having it work. And then the same thing with the charger. The charger can have different firmware versions. So you can see the interoperability problems that happen all across this part. And really, this is how everything kind of can fall apart. So what's needed to solve this problem? If you think about it, years ago, how did cloud solve this problem? They thought about terms of building observability platforms where they could basically have all in one spot logs that basically pull all the data together, all the logs from the six different systems, the raw logs all together into one spot. Basically summing up those metrics together into actionable things, and then having distributed traces, meaning that being able to trace the end-to-end log from the vehicle to the charger to the cloud backend to the credit card system and everywhere in between, and basically be able to visualize that all that entire flow. And then lastly, how do I fix it? So how do I profile what's going on, and how do I do alerting on it? And what I want to say today is there isn't a system that does this, quite frankly, at the moment. And what happens today is, for people who run EV charging networks, they have to log into the admin systems for each of these different things, even if it's available. So, for example, the charger itself, a lot of this data that's captured is literally captured on a text file that's stored on the charger. So it might not even be available to a cloud. And more importantly, in the data that's in the EVE, you might not necessarily be able to get what's going on. So really what I'm trying to say here is, what happens today is people who run these charging networks, they have 6 different UIs that they have to log into to get the logs, and then they literally have to download them to their machines and trying to manually put together line by line by line. Can you imagine going through 6 different systems log files and copying and pasting, putting that together? That's exactly what happens today, right? So what if we had a platform that basically provides a way to pull this all together, similar to what cloud has done, and build, a UI that you can visualize all this information, be able to pull that all together, and be able to alert on it. And so, just to kind of dive into what the complexity that it takes to do this, here's an example. I mentioned this before. Here's an example of what one of the data streams looks like. All right. So just this is a real example of the data, the log files that's showing the data that's flowing between the vehicle and the charger, and it's literally text and with timestamps, right? And so, and for one charging session, this is pages and pages and pages long, right? Because a charging session can go anywhere from 15 minutes to 30 minutes to 45 minutes, depending on the speed of the charger, right? And throughout, it's communicating back and forth. So this can go on for a long time, and you can see this is very ugly raw data, right? So that's problem number one. And then problem number two, let's talk about when the charger communicates to the cloud-based charge management system, via OCPP, which is the protocol. As you can see, this is another sample data set from this. Well, the nice thing about OCPP is it's a standard, and so it's all JSON based, and it's nice. It's not as bad. But the problem with it, though, is this can be pages and pages and pages, right? And this is only 2 of the 6 systems from that standpoint. And remember, what happens today is, the network operations center, they basically have to log into different systems and download stuff to their text editor and stitch this all together. So in order to put it all together, what you need to do is you need to do similar to what other, IoT or other, other, cloud-based observability platforms do. It's a log analysis problem, where you basically have the data sources all your logging sources. The 6 I just talked about, they can be text files, they can be, they can be JSON, they can be, they can be APIs, they can be various different things. So you have these different sources. You need to collect and ingest them in, probably near real time, so that way you can get the observability parts about it. And you can actually do alerting. You need to process and parse it. So using the example I showed before, with the text file, each one of those lines is critical data. What you need to do is you need to take each one of those lines, parse it out, and then find, almost do regex expressions to find what each parts of that each line means, and then so that way you can then use the timestamps to stitch everything together, and also use the information in the individual log lines to tell a story. You need to store this information not just for the short term, but also for the long term, probably for AI and predictive purposes. You need a way to basically be able to full text search these in certain cases, to find patterns and problems, and then you also need a way to do analysis, ad hoc analysis with it. And then lastly, if you've cleaned all this data and provided it in a nice, easy format, you need to then basically be able to visualize it, in a dashboard, make it a nice interactive piece, and then also probably build alerting on it to say, whether or not you're at falling below, 97% first time plug success rate or whatever that number is. So why could Doris be a possible solution for this? And this is one of the use cases that the Doris team, the VeloDB and the Doris team always talks about, right? And is log analysis. There's a white paper on the website that gives you examples of how others have done it in other industries. But the other thing is there's actually a playbook that you can follow for your use case. But really, from a technical standpoint, the thing that's really why it works well is it's designed for real time. The session before was about real time ingestion, and so it can handle massive amounts of unstructured and structured information continuously and make it available within seconds. And so then also the columnar storage allows for fast scans. So not only can it do traditional OLAP data warehousing use cases, it can actually do time series stuff really, really well. And then you can then optimize those specific queries for what you need as you go through the cleansing process. Compared to Elasticsearch or others, you don't need to learn a new query language for this. You can use SQL, meaning that it's more accessible. Your analysts can, your analysts, general, data analysts can use it, but then you also can turn on, a backend engineer if you want, and not have to have them learn something new. They can use SQL and the tools that they're used to doing that. And then the part we have found, we possibly found to be very helpful is the aggregation, how it can aggregate lots of data that is both structured and unstructured together, but still give you the bit of flexibility to be able to search that part, and then basically be able to offload that to hot and cold storage, but also being able to, from a cost perspective, be able to scale to petabytes. And the last thing is for commonly used aggregations such as error rates or request counts or common failure modes. The asynchronous materialized views are amazing, and they provide a way for you to roll this up without having to move the data between the different layers. You can keep it all stored at once and then have it aggregate to different views that you want, which is way different than some other data architecture patterns. So it's more like a lake house from that point of view. So what would this look like? hypothetically. So, once again, over here from an architecture standpoint, you could have the different data sources. You could pull those into, either through micro batches, for depending on if there's an API that you need to pull data from, or maybe you need to just pull raw text files off of different devices. You can do that through micro batches, but then you also have the ability, as data is coming in from the charger to maybe the cloud charge management system. If you want that to be directly streamed, you can use Kafka and Kafka Connect. But in the end, it all can end up in Kafka topics that as the landing zones. And then from there, Doris can then use its ability to, ingest the data from Kafka in near real time. And then from there, you once it's in Doris. One of the patterns I really like in data engineering is the medallion architecture. So ingest, basically get the data in to Doris, and in the bronze layer, just the raw text files, the raw JSON, whatever it is, and then you can then transform that into silver and gold. Silver being a lot more cleaned, basically reusable use cases that can be used from multiple different data products. And then gold, you can then aggregate to very specific patterns, such as what are your success rates, what makes the models are the most successful from a charging perspective, and what areas do we need to investigate to possibly go and figure out. So assuming that all this data is coming in near real time and transforming to these gold and silver layers, you could then do the really, really powerful stuff that we've seen work really well in the cloud, which is you could build a rules-based alerting engine to basically say, based on the specific failures that are happening, go ahead and do alerting. But you could also use this data to actually automatically classify, in this really long page of data associated with a charging session, why does it fail? And specifically target the real root causes of why it fails, and then basically be able to take action off of that through the alerting pieces. And you could actually build a nice UI on top of that. It doesn't have to be Superset or Power BI or one of those, but you still have the option to do that if you'd like, maybe for doing ad hoc analysis, or maybe for doing roll up type reporting. And then last and not least, you could then use AI and LLM possibly, or anomaly detection to basically be able to proactively be able to figure out why a session is going on, why a session is failing, or find patterns at a time rather than waiting for someone else to do the analysis. And all this could basically run on EKS, Amazon EKS, or it could be run on GCP, or it could be run on any other cloud provider that's out there today. So this is a possible way of approaching it, and all this could be achieved. And so really, from a Doris standpoint, this is just showing you the different layers. Once again, just getting all the log sources, ingesting the data, providing the ability to split out query nodes from backend nodes, and then visualizing and using the data how you need to as appropriately. And with that being said, I'm just going to bring up a sample what an observability platform could look like. So as you can see here, the data, you can see in real time, the data that's being streamed in from the field, how much total power is being consumed across your network, how many active sessions are going on, the total, the success rate, how the average response time to initiate a charging session, what's the success rate on the network over time, and then more importantly, what's the root cause failures that's been automatically classified based on the classification engine. And and then furthermore, you can see which chargers are doing well, and then what alerts you need to go through and investigate based on all the data being pulled together into one spot. So anyways, but in the end, this is a very, very powerful application for Doors, and I think it's a very cool and unique use case specifically for a growing industry worldwide. So with that being said, I'll go ahead and stop and turn it back over to Shirley.